has an atmosphere enough to fly a helicopter. And it is cold out there, so that what they have, what is on the surface, is solid ice, and over that are liquid hydrocarbons, which you would use for fuel here in our home. But over there, it's liquid rain, and lakes and rivers, and we will be looking at the geology of that before we send the helicopter out there.
So you're on this amazing journey from the very distant early universe all the way to our own solar system, but this has also been a personal journey for you. You've been working on Webb since the very beginning of the mission, is that correct?
I have. Since '95, we had our first conversation, but people were even dreaming and imagining way before that what we needed. And you could tell even before we launched the Hubble what were the possibilities, and we learned that we would need an infrared telescope that could do things that Hubble could not do.
Well, John, I've been an admirer of yours for many decades now, and it's an honor to be with you on this part of the mission. So thank you so much for joining us. Best of luck on the launch and the mission ahead.
And thank you for asking all these great questions.
The Hubble Space Telescope delivered profound insights about our place in the cosmos. But perhaps the biggest takeaway from Hubble is that we've only just scratched the surface. Hubble gave us the best ever views of stars and planets forming inside vast, dark clouds of dust. But as soon as we had that data, we were asking new questions that needed better measurements, clearer images. Hubble was also able to capture images from galaxies so far away. Their light took 13 billion years to travel to us. These distant galaxies are just tiny dots in Hubble's images, tantalizing scientists with clues about how the first galaxies formed. In order to pursue a better understanding about the earliest days of the universe, we needed to build a better time machine, and that's Webb. So I'm going to be rejoined here by Nicole and Macarena, and this is our chance to talk a bit about building that better time machine. You know, what about the technology of Webb? So there's so many aspects of Webb to start off with, but maybe again, going back to the theme of infrared. The design of this telescope is so different because we had to use infrared light, heat light. So tell us about some of the challenges of, for example, why does it have to be so cool? Tell us about infrared light in the design.
Right. Well, I think we've heard already just how cool it has to be. It's around or below 50 Kelvin, and that's minus 370 degrees Fahrenheit. Actually, below that is what it operates at. And that's very cold. And the reason we need it so cool is because we don't want the telescope itself to detect itself. Because there's several instruments on board. There's 4 different instruments, and there's some moving parts, and so you need things to be cool because you want to detect these faint signatures from either an exoplanet atmosphere or faint light from the earliest stars and galaxies. So you just don't want to detect your own telescope.
Now, Macarena, you are the instrument and calibration scientist for the coolest instrument.
It is the coolest
on Webb.
Yes.
MIRI. So tell us a bit about MIRI and why it needs to be so cold.
So MIRI, it's a really unique instrument, and it's a great example of this collaboration we have in this mission because it's half European, half US. And so MIRI is the only instrument on board that uses the mid-infrared light. And the mid-infrared light is a bit redder, a bit cooler than the near-infrared light, and so because of that, MIRI needs to be colder in order to detect that very faint signal from high-redshift galaxies or protoplanetary disks, etc. So because of that, it's the only instrument on board that has a cryocooler. So it is not only the passive cooling from the sun shield, it is active cooling, and it brings it down to about minus 450 Fahrenheit. So it's really extremely cold, a few degrees above the absolute zero.
And we were talking about you don't want the telescope to be so hot that it's basically giving off its own signal, its own radiation, and that leads us to why it needs to be in space, right? So tell us a bit about why do we need to launch this thing into space to see these wavelengths?
Well, again, it kind of goes back to atmospheres because Earth has an atmosphere and there's water in Earth's atmosphere as one example. I mean, there's a lot of other molecules, but basically in the infrared, at the wavelengths that we want to observe some of these stars and planets and galaxies, those wavelengths are actually where Earth's atmosphere is opaque. So with telescopes located on Earth, even at higher mountains where they try to get above the clouds or atmosphere sometimes, there's still residual atmosphere that we're trying to look through and peer through. So in order to see the full infrared wavelength range at a very high sensitivity as well, we need to go to space.
Absolutely. So we talked a bit about some of the power of techniques like spectroscopy. We've heard Dr. John Mather talk about it. So let's go a little bit more into the details of how spectroscopy works and why it's so powerful. Continue.
Oh, sure, yeah, I can keep going. Well, with spectroscopy, we heard, so visible light, again, is kind of, it's a rainbow of colors that we don't see naturally. But if you use something like a prism, you can separate out that light and see all the colors from, blue to red. But then the infrared is redder than the human eyes can see. But you can still do the same technique where you have spectroscopy tools or instruments like Webb has, all these spectroscopic tools, so that we can break up the infrared light and look at certain colors, if you will, so that we can see certain features that we are looking for, whether it's the right wavelength where, a galaxy might be bright or where water is absorbing in an atmosphere.
So, Macarena, MIRI has many different capabilities.
It does.
And in fact, it has one that I believe it's something different called coronography as well.
Yes.
Tell us a bit about all these ways that we're going to detect different signatures from planets. Tell us
So
about MIRI.
coronography, it's an amazing technique, but essentially it simulates an eclipse. So when we have a very bright star with planets around, for instance, usually when you take an image, the stars outshines the light of the planet, so you don't see them. But with MIRI and with other instrument NIRCam as well, you can actually block the light of the star and dim it, and then you see the planets around. And it's really a technique that's going to be very much used and to do, like in this image, direct imaging of planet.
Well, thank you so much. We'll be back to talk to you more with some social media questions. Thank you very much.
Thank you.
NASA and its partners began developing the Webb telescope years ago, growing from an initial inspiration to a design, then schematics, and finally reality. What started as a big dream for studying the origins of the universe required best-in-class engineering expertise to transform into something real. Let's take a short look at the very long story about the earliest days of the James Webb Space Telescope.
Before the Hubble Space Telescope even launched, scientists were already discussing what should come next. Ideas for what was then called the Next Generation Space Telescope evolved throughout the 1990s, and by the end of the decade, NASA had a preliminary plan. Construction of the James Webb Space Telescope began in 2004. Beryllium was mined to create the mirror segments, which technicians polished and coated in a thin layer of gold. Meanwhile, engineers designed and built new science instruments in the US, Europe, and Canada. Every step of the way, there were reviews and tests to make sure each part could withstand the rigors of spaceflight. By the early 2010s, the team began bringing individual components together at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It was there that the mirrors and instruments began to coalesce into the grand machine we see today.
We've said before that the James Webb Space Telescope is an incredibly ambitious mission. Big ambitions come with big challenges, and that's certainly been the story of Webb. From the beginning, the design of this observatory has been a balance between the boldest questions scientists have dared to ask and the cutting-edge technology that our best engineers could offer. The design for Webb evolved from earlier ideas of what a telescope could be, another example of the delicate balance between desire versus capability. To get a better understanding not only of the mission's goals, but also the mechanical guts of the observatory itself, I recently got a chance to speak with a pair of engineers who know the anatomy of the Webb telescope better than just about anyone. I'm here with Keith Parrish, a senior engineer on the Webb mission. And Keith, you brought something to show us today.
Yeah, yes, I did. So conceptually, Webb Sunshield is actually quite simple. All we need is 5 tennis court size pieces of this material outstretched to protect the telescope from the sun. So what I have here is an actual sample of that material. This is just Kapton.
It's so light, yeah.
Yeah, it's an industrial, you can buy this and it's commonly used. And what we do is we buy it for Webb. We seam it all together in small pieces and then we actually coat it with special coatings to give it the what we call the thermal properties we need in orbit. So this one has a nice pink or purplish kind of hue to it, and the reason it's purplish in hue, we use this on the sun side, and we actually put a silicon material on this Kapton, and then we actually put a little bit of a metal in it. And what that metal does is it gives us a nice electrical conductivity. We don't want any surface charging building up. And the other thing is this silicon coating actually drops the temperature of this layer. So, and also it's very durable and can survive, for many, many years in space.
And then this whole thing has to unfold somehow, where we can actually see that behind us.
Exactly right. So if you look at that animation there, unfolding there, so it's actually S-folded up. Almost like a fan. We call it S-folding. And once we get it all folded up, we secure it to a structure by actually pinning it for launch. So, a huge shout out to our mechanical engineer and our entire Sunshield team, because they've come up with some really clever ways to secure this for launch, unfold it, fold it, and then, ultimately get it safely deployed in orbit.
That's wonderful. So speaking of unfolding and all these pins that need to release, let's go over here and talk to James Cooper. You're going to show us what's going on there.
Yeah. Hi. So I have here an example of a non-explosive actuator. We have 178 of these.
These are all these little pins we're talking about, right?
James Webb, right?
Yeah.
107 of the 178 are the membrane release devices. And we use this type of actuator because it produces a very low shock when it's released. And the animation shows conceptually how it works. We send an electrical signal through either one of our connectors. We use both, but either one of them can cause the release to happen. It melts a small wire inside, and then we have a spring that unwinds and allows two halves of a split nut to separate, and then our pin can get extracted. And so in the case of the MRDs, it's a spring-loaded pin that pulls to release the folded membranes. In other places, we would be bolting two pieces of structure together and then releasing them so we can deploy them.
And the Sunshield itself has 107 of these?
107 MRDs that all have to work.
Every single one
Every
has to work.
single one has to work. And 178 of this type of device in various configurations around the entire observatory.
Right. Well, if we go over here, we've got something sort of lovely waiting for us, a big gold hexagon. So to tell us what we're looking at, a sort of a model here of a mirror segment, right?
Right.
Yeah.
Full-scale, single segment, one of the 18 mirror segments on James Webb. The real ones would be machined out of a single piece of beryllium to the exact curvature we need. And then once we're deployed on orbit, each segment can be individually focused to make it act as a single perfect mirror.
Now that coating, tell us about this gold coating here.
Yeah, so this is coated with a very thin layer of gold. It's only a few hundred atoms thick of gold, and that gold is really good because it gives us a reflective property in the infrared, and that's really what Webb is an infrared telescope, and we need that Sunshield exists to cool this entire telescope. So this mirror actually runs about minus 400 degrees Fahrenheit on orbit. If it were warmer than that, the infrared energy coming off of this, that heat energy would swamp our detector system and our instruments. So that entire Sunshield exists to cool all 18 of these down. And again, this gold coating is what helps with all that reflectivity to make it perform even better.
Well, that's wonderful. So now you put it all together, and we have a smaller mock-up here, the Sunshield, the mirror. Tell us what we're looking at here.
Much smaller. So, yeah, this is our entire observatory fully deployed on orbit. And you can see the Sunshield here is a large feature. You can see all 5 layers that I talked about earlier. And it's the separation of those 5 layers which lets heat energy escape out to space before it eventually gets to this cold layer. Again, that entire telescope is running minus 400 degrees Fahrenheit, and the way we get it that cold is this side is shaded. The telescope is looking to the deep universe, which is near absolute zero. And then again, this layer here, we've got about a 500 degree temperature drop, so this telescope is also looking at this layer here, which is nice and cold. So that's what lets us, harness thermal physics to cool this down to those really, really cold temperatures. Again, you can see our booms, which are fully deployed and stretching this out, and then ultimately all folds up and gets stowed into this structure for launch.
Right, so the membrane release devices would be along the back side of these structures on the forward and the aft side. And we release them in rows so that we can sequentially start to unfold the membrane once those pins are pulled out of the way.
Well, that's wonderful. Thank you so much for joining us, and best of luck on the launch. I'm very excited.
Yeah, thank you.
Okay, let's get a live launch status update from NASA commentator Rob Navies at the launch site. Rob, how are things in Kourou?
Well, thank you, Michelle, and Merry Christmas from the Jupiter Control Center here in Kourou, French Guiana. You are looking live at an Ariane 5 rocket on its launch pad, ready to send the James Webb Space Telescope on the initial phase of its journey. The fueling of the Ariane 5's first and upper stages began before sunrise, and in the last few minutes, mission controllers here in Kourou and at the telescope's control center at the Space Telescope Science Institute in Baltimore conducted polls, with all positions reporting they are go to proceed into the final phase of the countdown. Launch controllers have been monitoring weather conditions throughout the night, keeping tabs on clouds and wind speeds, both at ground level and in the flight path of the Ariane 5, ensuring that all of the precise commit criteria are acceptable for launch. Right now, we have a green board, no issues as the countdown proceeds, no issues again being tracked by the flight control team here in Kourou. By the way, our broadcast today is a collaborative effort between NASA and the European Space Agency. So that's it from now. From the Ariane 5 Mission Control here in Kourou, we'll be back with you soon. For now, let's go back to the Goddard Space Flight Center and Michelle Fowler.
Thank you very much, Rob. So Webb asks big science questions. It demonstrates astounding technology. It inspires and excites people to dream and wonder. And the spark of inspiration is the ignition of creativity. Kids all over the world have a natural affinity for Webb's big pursuits. And now we have a collection of young artists ready to showcase their work.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope. NASA is hosting an Unfold the Universe Art Challenge. Use your imagination to share what you believe the Webb telescope will find.
I believe that the Webb's telescope will see galaxies, stars, planets, the moon, and don't forget our star, the sun. Up in the sky, really high, it's space.
Ooh, space. Thanks, Greta. Good job.
This is my picture of space. Hello, my name is Gabriel. I am from Romania. This is how I imagine space. Hello everyone, good morning. This is the drawing of distant galaxy that can be seen by James Webb Space Telescope. Hi, my name is Anastasia, and this is what I do when I think the telescope will look like, what the telescope will see. I drew the Earth, the Sun, a new planet, a black hole, and stars.
So we've been fielding social media questions from viewers all over the world this morning, and let's take a couple of minutes to share some responses. There's been a couple questions about how long will it take for images to come out, and there's a lot of things that need to happen before the images are coming. So Macarena, why don't you take us through some of that?
Yes, so for the first scientific beautiful images to share with the public, that will take 6 months. And the reason is because it is, so we launched today, it takes a month to take to the orbit place, to the Lagrange 2 point, and then we have a whole period of cooling down the instruments, aligning the mirrors, and making sure that all the instruments are ready to do science. So the whole process takes 6 months, half a year.
And also all of those 18 segments of mirrors, something needs to happen to get them all working together too, right?
Exactly, because initially you launch with 18 segments and they work separately. So you will take, if you observe one star, you will get 18 little points. So there has to be a process where you take images with NIRCam, which is one of the cameras on board, start moving the mirrors slightly to make them work as a single one, and then by the end of this iterative process, you go from 18 points to a very sharp, pristine single point source. So all mirrors act as a single one.
So let's see, we have a question from LV coming in on Twitter. Will Webb be able to enhance detection of comets, asteroids, or meteors that enter our solar system? So that seems we've got a planetary person here.
Sure. Yeah, well, Webb does have a special observing mode where it's able to track these rapidly moving objects, because compared to these distant stars and galaxies, asteroids and comets, they move pretty quickly. And so Webb will be able to do this so that we can study material that's outgassing from them and learn more about what they're made of.
So let's see, there's just so many good questions, so we only have time for a few more. So one is from Kristen Rodriguez on Facebook. How long will it take James Webb to reach Lagrange point 2? And you might also just explain what is Lagrange point 2?
So it takes a month. I think it's actually 29 days to get there. And the Lagrange point is this very interesting stable point. So the gravitational pull between the sun and the Earth creates this point where it is stable, and you can, as we can see there, Webb can orbit around the L2 point in a very stable orbit, only needs a little bit of corrections once in a while, and it can always have the sun shield protecting the telescope from the radiation of the sun. In a full year, you can observe any object in the sky, and it's a continuous observation.
Well, thank you very much. We'll hopefully come back to a few more questions later.
Thank you.
So this is a big mission with a cast of thousands to bring it to life all over the world. As we get closer to launch, let's take a brief look at the main locations where Webb took shape on its journey to space.
Inside the massive high bay clean room at NASA's Goddard Space Flight Center, engineers assembled the 18 gold-covered mirror segments into the backplane of the telescope and integrated the 4 science instruments contributed by international partners. To simulate the harsh environment of launch, they went through vibration tests and acoustic tests. And to simulate a space environment, the instruments endured cryogenic testing in a large thermal vacuum chamber. But it wasn't large enough to hold both the instruments and the mirrors, so the telescope boarded a plane to Houston, Texas, to visit the only thermal vacuum chamber in the world big enough to fit the entire assembly. Chamber A at the Johnson Space Center was originally built to test the Apollo spacecraft, and half a century later, it provided a grueling 100-day test for the Webb telescope. Next, the telescope traveled to Northrop Grumman's facilities in Redondo Beach, California to meet up with its other half, the Sunshield and spacecraft bus. Fully assembled at last, the entire observatory went through yet more tests, many focused on making sure the spacecraft could properly fold up for launch and unfold in space. Then in September 2021, Webb caught a ride on a specialized cargo ship and set out on a 16-day voyage to the European Space Agency's spaceport in Kourou, French Guiana. According to its travel itinerary, that's Webb's last port of call on Earth.
Once Webb gets into space, we're going to have some exciting things to tell you about what happens next, from its extraordinary engineering to the thrilling scientific adventure it's about to enable us to undertake. But launch comes first. And for that, I'm going to turn it over to Katie Haswell, our host at the launch site, and one of NASA's most recognizable voices, launch commentator Rob Navis. It's all yours, Katie.
Thanks very much indeed, Michelle. Well, it's all looking very good here at the spaceport for a Christmas Day launch. Operations running smoothly, the countdown ticking over nicely. All the systems are green and we are go for launch. You can see there we're looking at launch pad number 3, the James Webb Space Telescope, inside the very top of the rocket in first class with its seatbelt on, waiting patiently for liftoff. That's scheduled in about 32 minutes' time. I'm in the Mission Control Center here at the spaceport, the nerve center of operations. We're about 10 kilometers from that pad, and behind me you can see it's a laser focus here in the control center with the mission control centers all on console there as we get closer to launch. We call this the fishbowl behind this protected glass. And up in their skybox here in Mission Control are NASA's Rob Navius and the European Space Agency's Luce Fabregat, and they're standing by to take over the commentary about 15 minutes as we get closer to launch. First of all, though, let's check in on the countdown and let's see how things are progressing with Stefan Israel. Stefan is the CEO of Arianespace. Arianespace is the company responsible for getting our telescope into space today. Stefan, thanks for joining us. No pressure.
Good morning, Katie.
How are things looking?
So we are now 31 minutes before liftoff. So far, so good. Ariane 5 is ready. Webb is ready. The range is ready. And the weather is green.
Well, that's good to hear. So what can we expect to see? What's going to happen?
Yes, so in the 30 coming minutes, we will make the final operations. 10 minutes before liftoff, we will have the final authorization of the weather. And 7 minutes before liftoff, we will enter in the famous synchronized sequence.
And, I mean, how's everyone feeling? I'm guessing everyone's...
We launched for humanity this morning from the Guyana Space Center. You know what Webb is about? After Webb, we will never see the skies in quite the same way.
It's an important project, isn't it, for everybody?
It's a very special mission, but we have delivered already 111 times with Ariane. This is the 112th Ariane 5, so we will deliver this morning.
And everybody there in the control center, cool, calm and collected. Stefan, thank you very much for having taken time to step out of the fishbowl for us. So you can head back now into the fishbowl and take up your position. Stefan Israel, thank you very much indeed. Stefan, of course, heads up what we call the flight desk, which is the authority that takes all the final decisions in the event of unplanned situations. Now, we are in French Guiana. We're on the northeastern coast of South America. We're in Amazonia. It's hot. It can get a little bit sweaty sometimes, and there are lots and lots of mosquitoes. But somebody who knows it very, very well is Raphael Chevrier. Raphael is a rocket scientist, or a rocket expert at least, from Arianespace. Thanks for joining us, Raphael. Tell us a little bit more about French Guiana.
Well, French Guiana is a French territory that borders Brazil. It's located in the Amazon rainforest. 97% of the land is covered in trees, so that's why it's so green and beautiful. And you can totally imagine that the wildlife there is absolutely incredible. This is actually one of the best preserved habitats in the world.
And of course, it is in the jungle, and yet it is actually the European spaceport. So what makes this location in South America so important and so relevant?
Well, there are several reasons for this. First, we are on the coast. It means that we can launch over the sea from north to east without having to fly over inhabited area. So this is very convenient to reach any kind of orbit. There is no hurricane here, big tropical storm, there is no earthquake, but more importantly, we are very close to the equator, so that we can benefit from what we call the slingshot effect given by the rotation of the Earth. So let me take this globe. Basically, here on the equator, we are all traveling at roughly 1,000 miles per hour. That's very convenient. Of course, we don't feel it. If we were on the poles, that speed would be very, very close to zero. It means that when Webb is right now on the launch pad, inside the fairing of the Ariane 5, it's already traveling in the right direction, and we can use this extra boost to get us into space. That's also very convenient for Webb, because doing so, it can save its fuel and increase its operational life in orbit at 1.5 million kilometers from here.
And that really is important, 1 million miles, isn't it? And so there's a real proper slingshot effect. Yeah. And the facilities here are ultra high-tech, and that's exactly what Webb needs, isn't it?
Yeah, that's very convenient for Webb. It's also located in a nature reserve. So this is the perfect meeting between nature and technology, and people come from all over the world to work here. But one thing that's been very important for Webb is cleanliness. Because you know that one speck of dust could alter the vision of the observatory in space. That's why we have been extremely careful in keeping a pristine environment in all our facilities, from Webb's arrival in French Guiana to sealing it inside the rocket.
So let's talk a little bit now about the Webb Space Telescope. I really don't think you need me to tell you that it is the product of a feat of human ingenuity. And you don't get to make a telescope as complex as the James Webb telescope and as remarkable without tremendous amount of collaboration. And the James Webb Space Telescope is indeed the product of a partnership between 3 space agencies who came together to create it, NASA, the European Space Agency, and also the Canadian Space Agency. So here to talk about that now is Greg Robinson from NASA. Greg, thank you very much for coming to the floor, out of the fishbowl as well for us. And we're talking serious teamwork here, aren't we?
Yes, Katie. We've benefited from an amazing partnership with the Canadian Space Agency and the European Space Agency. Over the life of the development, we've had more than 10,000 people actually touch Webb, 29 states in the U.S. and 14 countries across the globe, and not to mention the amazing industrial base across the globe that have benefited here. In order to do bold missions like this, it takes lots of resources and lots of expertise, so we maximize everyone's expertise.
And how did this bold mission get onto an Ariane 5 European launcher?
So as part of the partnership, the Canadian Space Agency contributed science instruments, and they're incredibly important for this mission. And so did ESA, science instruments, and the amazing Ariane 5 that we will see take us on this journey and put us in the right direction to get to Lagrange Point 2. And we're looking forward to that.
It's a tremendous atmosphere here, isn't it, in the Mission Control Center? There's a real buzz here today. I wonder how you must be feeling, Greg. I mean, it's got to be a very, very emotional time knowing that your telescope is sitting there on top of the rocket getting closer to launch.
It's certainly amazing. Often talk about the butterflies, and people keep asking me, have they started? Have they started? And yes, they're starting. And when we get to about 20 minutes out, they will start flying a lot. So the excitement is just amazing.
The excitement is building, and of course everyone very cool, calm and collected. Thank you, Greg Robinson. You can take your position back in the fishbowl now because I know you've got a lot of work to do in there. Greg Robinson, thank you very much indeed for joining us. So the Ariane 5 launch vehicle is the heaviest lifter in the Ariane 5 Ariane family of launchers. And Raphael, she has got an incredible track record, hasn't she, of success?
Yeah, this is a very reliable and successful rocket. Webb is going to be the 112th Ariane 5 to be launched. And the very first Ariane, the Ariane 1, took off exactly 42 years ago. Yesterday, this was on Christmas Eve, 1979. Good symbol.
Yeah, and hopefully we're going to get a good Christmas present today as well. And I mean, the rocket is also, you don't get to build a rocket like this without collaboration either, do you?
Of course, just like Webb, actually. In fact, 12 different countries have been participating in the development of the Ariane 5, with Ariane Group now being the industrial prime.
And we have a scale model right next to you, Raphael. Why don't you talk us through it? The rocket is made of sections, and we often call those stages, which is what you might hear during the commentary.
Exactly. So first you have the 2 boosters, solid boosters, that are located on each side of the rocket. They will provide the main thrust in order to literally push the rocket against the gravity of the Earth. Then you have these big tanks that form the main cryogenic stage, with the main engine Vulcan at the bottom.
And then you have the Webb telescope right at the top, inside the fairing.
It is right there on the launch pad, and together they are put on top of the 3rd stage, a cryogenic stage, and it is this upper stage that is going to place Webb into orbit.
And what about the engines? What are we going to see at liftoff?
At liftoff, we first see the main Vulcan engine ignite first. We do this because we want to check it's working properly before we switch on the solid boosters 7 seconds later. Once it's done, there is no turning back. The rocket is going to lift off. And so, yeah, that's very, don't be surprised. Don't be surprised if you don't see the rocket lifting off for 7 seconds. That's time for the rocket to actually warm up before soaring into the sky.
So once we light the touch paper, you can count to 7 before it actually lifts off. Now, one of the advantages of the Ariane 5 vehicle is that it can be modified, and that's exactly what we've done for today's launch. We've had to make some changes for it to be able to host the Webb satellite. And joining me to talk about that is somebody who, the right person for the job indeed, because he was in charge of those changes, Daniel de Chambre from the European Space Agency. Thanks for joining us, Daniel. What did you have to do?
First, we need to recall that Webb will be the largest payload to be ever accommodated on IL-5. It fully occupies the volume of the fairing, with gaps as small as 10 centimeters for a diameter of 5 meters. It is the reason why we had to develop a specific integration procedure to ensure that there is no contact with them. After separation, during separation, the venting system of the launcher has been improved in order to balance as much as possible the inside and the outside pressure of the fairing. And this is due to the fear of depressurization shock, which could damage the delicate layers of Webb thermal shield. After separation, due to the fact that some equipment of Webb are very sensitive to sun exposure, the roll control of the launcher will be tuned in order to make sure that Webb is always oriented only one face to the sun. And in addition, to avoid any hot spot, the launcher will create some oscillating movements, like a barbecue mode, to avoid any overheating. And after Webb separation, there will be a specific end-of-life maneuver to be applied on the upper stage in order to put it on a liberation orbit around the sun in order to avoid collision in the long term.
Thank you very much indeed, Daniel. So we'll hopefully see the upper stage rocking in space. Not quite all the way around like the familiar barbecue, but a slightly different movement. Listen, gentlemen, thank you very much indeed for being with us today. I know that you're busy. You've got jobs to do inside the fishbowl, so I'm going to send you right back there now, and very best wishes for the launch. Thank you.
Thank you.
Our telescope has a long journey ahead of it. It's got to travel 1 million miles to its destination in space, its working zone, where it's going to start telling us all about our universe. It's already started that journey because it's traveled to the launch pad from Los Angeles. After final tests were concluded in Los Angeles, Webb was packed into a special container and transported along the LA 405 freeway, which had to be closed because it's so big. It traveled on a special ship. A lot of spacecraft will come to the French Guiana launch site by plane, but Webb was too big for that, so it had to travel by ship, and it went through the Panama Canal. Up through the locks. And it took 16 days to get to the port in Kourou, where it was unloaded and traveled to the spaceport. That's not the real Ariane 5, that's a model, just outside the Jupiter Control Center, actually. It was unpacked very carefully in the facilities that Raphael was talking about. And then fueling started, and of course the teams had to wear special suits because that's a dangerous job. And then it was placed all the way on top of the Ariane 5 rocket. It was encapsulated inside the fairing and sealed, and then it was rolled out to the launch pad 2 days ago. From the vehicle assembly building to the pad along very special rails. Very, very slowly through the Amazon rainforest. It was raining at the time, and that was 2 days ago, and here we are now, 17 minutes and 46 seconds to launch and counting. All systems are go here at the European Spaceport in French Guiana. We have 3 control centers on the job today. We have the Mission Control Center here. We also have the Launch Control Center, which is about a mile from the pad. And then we also have the Telescope Control Center, Mission Control in Baltimore in the US, and that's where the operational teams are standing by to take over the telescope operations. Once it's released from the mothership, that will be about 27 minutes after launch. And they'll be controlling the Webb telescope for the rest of its life. Very important job. The James Webb Space Telescope is a truly remarkable observatory. People have been working on it for over 2 decades. Some people have been working on it for their whole professional lives. Thomas Zurbuchen is the head of science at NASA, and he's joining me now just to talk about it. Thomas, or Dr. Z, as we can also call you. The day has come. All these decades, all this time, all these people working on the telescope, and here we are, 16 minutes and counting to launch. It's a big day, huh?
Oh, I'm so amazed.